Hello and welcome to TidyX episode 29. So this week's TidyX, we're going to discuss more Tidy Tuesday submissions, and we're also going to go through a model that Patrick built that I think is pretty exciting, and I think it's pretty cool. So definitely stay on to watch this entire video. We cover a lot of really great information about using R to create models and do that sort of stuff. All right, so the Tidy Tuesday dataset this week is on Himalayan climbing expeditions. This comes from the Himalayan database, where it's a compilation of records of all expeditions that have happened in Nepal, Himalaya. It was fairly rich. A lot of people were doing some pretty cool and, to me, visually incredibly striking plots. Like, it felt like this week there was a kind of a slant towards models and people doing model type stuff, but then there was just like, I don't know, blue is like one of my favorite color. And the palettes that people were choosing this week kind of trended towards more blue, but then it was like ice blue and then white. I thought they looked pretty gorgeous.
Yeah. I was kind of surprised there weren't more maps. I thought there'd be some maps of like tracks, like hiking tracks and stuff.
See, I thought so too. But it looks like there was a lot of like time series type stuff, so I think people kind of jumped on that and did that sort of thing. So the one that we picked this week to go through and explain kind of focuses on the palette. What we want to focus on is the palette side of things. This is from Kaylea Haynes, and she submitted this, I think, visually incredibly striking graph showing the different termination reasons or successes across the time series that we were given for the data here. So it starts, 1900 or so. I mean, you can definitely see people are, increasing the number of expeditions that are happening in the Himalayas. It's binned. It's got this really, I think, pretty cool color palette here. I don't know. When I saw it when I was scrolling through Twitter, I was like, oh, wow. That, caught my eye. I was like, we're going to have to go through this and explain this.
Yeah. Super cool.
Yeah. So we reached out to Kaylea. Her code is on GitHub right here. So you can go pull it here from her GitHub. So we pulled that down and have it in so let me quickly restart my R session because we went through this to make sure we understood it all. And we copied her code in here for us to go through and explain. All right. So she has a nice little header here on her R script where she's describing what the data set's from, where she got it, what the data set is and what she's trying to do, which is a stacked bar chart for termination reasons. And then she also, she used this colorfindr package, which she came across, and she actually is putting some notation here. Actually, I'll zoom in. I'm kind of far out. She's thanking somebody, Anna Henschel, for helping her find that. And so that's kind of a nice thing to put into your scripts as well, is when you come across stuff that you're learning from other people, definitely throw in the link if you go to Stack Overflow or something like that, because it'll help your future self as well. So if you come across it and you're like, what am I doing here? What is this code doing? You can just copy it and paste it off of Stack Overflow, which I also do not suggest. You should definitely go to Stack Overflow for help, but try to understand what they're suggesting you do when you're copying it over and stuff like that. But putting that in a comment is really going to help your future self so that you can try to go back and look at it if it stops working, so you can try to understand the logic of the poster itself. And do that. Sorry, that was just kind of a sidebar there, getting on that. So then she loads her libraries first. So we've got library colorfindr, which is the library that is going to be used to create the palette, and then library tidyverse, which is used, for all our data manipulation needs. Next, she's using Tidy Tuesday R. Thumbs up. Like that, and she's loading it. So she has it listed twice here, and I think that's just because that's how Thomas shares it on his every week, is the two different ways. You only need to load it in one way, so you can either load it with the ISO date, so year, month, day, or the year and the week of the Tidy Tuesday. So we'll just run it once there so we don't download the data set twice. And then she extracts the expeditions data set out of it. Though there are more. There are peaks, members, and expeditions. All right, so this is the piece here that I thought was the really cool, the cool piece that kind of shaped the rest of the plot visually for me. And this is extracting the color palette out of an image. So I had to make some edits here because of the way that we have our directory set up. But really what she's doing is using get colors on a JPEG and then using this make palette function to create a palette based on the colors that exist in the JPEG. And she's asking for n colors, and n colors is the length of the unique of the expedition's termination reasoning plus 5. So what she's doing here is she's pulling out, okay, the expedition's termination reason field, and then taking unique, so you only get the list of unique reasons that an expedition might fail, getting the length of that, so that n number of expeditions, then she's adding 5 to that. So let's actually quickly take a look at the image itself, because it's also pretty striking. I mean, I think that's where you get the blues up here on the right, you get the snow-capped mountain there, you get some of the ground there. So it's going to have a lot of really good colors to pull out of this to then throw into the plot. All right, so we'll close that out, and we will run the code there. And so it's going through, it's reading it all, pulling in the palette, and then I think it has this nice feature where it actually also prints out all the different colors you get out of the image for you there. All right, so then what she does is she actually wants to subset, because she added 5 here, so she's now got more colors than she actually needs for her plot. So she's going to be subsetting to keep basically 4 less. So she added 5, so now she's going to do 5 to the length of the color palette to only keep this set. So it's going to drop these first four bars here. When she runs that, you can print it there. Colorfindr, we're actually going to hack into it a little bit. If you use 3 colons, you can go in and use functions that live underneath the surface that you're really not supposed to be using, but we're going to do that now. So do as I say, not as I do. But I wanted to show you what that the color looks like. So this is the actual palette that she created out of the image that she's then going to be using. So this is the original full palette, and then this is the subset. So it's a little bit more muted. It kind of removed like the big bright blues out of it. So then she's going to actually jump immediately into creating her plot. Patrick, do you want to take us through this?
Yep, the plot here is pretty stock ggplot tidyverse type work. She's got her expeditions data set. She's going to round the years so that she gets half decades with this cool round any function. Neither of us have heard this or have used this rather. We typically do this I think in the next script, in my script, I have a way of finding the decades, but it's a little bit messier, and this is nice little function. She then groups by the rounded year, the half decade year, and the reasons for termination, and she does a count. You probably could have taken both of those, round year and termination, and just put them in the count and got rid of the group by if you wanted to shorten up one line of code, but either way it still works. So same type of deal. Then she's doing a group by again, another group by termination reason, and she's mutating the sum of the reason for the termination. So that's going to get you the totality of the counts so that they can be plotted in this stacked bar plot. She arranges descending by that termination reason count, so the highest values will be on top. And then she's going to, so there you go. Obviously, success happens more often than not. So,
which is good. Otherwise, I'd hope that we'd maybe stop trying to climb if most people were dying usually.
Yeah, exactly. So she arranges the success. So there you can see, obviously, success by year. So 1910, 1930, yada, 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 all the way down. Okay, then she ungroups her data and she creates a mutate. So she's going to add a new variable onto the end of the data set called termination reason. So she's basically just using this to set her factor levels. So she wants her factor levels to be set by the unique termination reason. Ordered equals true, keeps the natural ordering that's already in the data set there. And then she starts the plot. So ggplot, she creates a geom bar. You could have used geom. You could use geom call as well. We've used that in the past. Either way, they produce the same thing. The only difference is if you use geom bar, you have to pass that stat equals identity argument so that it knows what it's counting up in the bars. So if you use geom call, you don't need that. But so she used geom bar. X is going to be the half decade. Y is the n, which is the count value in the third column of that data set. She's going to group by the termination reason, and she's going to fill by the termination reason. So that's going to be filling the color palettes that Ellis pulled out earlier from the JPEG. Stat identity is going to give you the true counts. And then position stacked, obviously, is how we get that cool stacking of the bar plot. The scale fill manual is just basically saying that, hey, we don't want R to choose the fill colors. We're going to choose the fill colors for it. And those are going to be the colors that were selected from our color palette filter up at the start of the at the start of the script. Theme classic is just going to, it either like gets rid of the grid lines or like grays them out substantially or something. I can't remember which. I think maybe theme light gets rid of the bars altogether, and theme classic makes it.
You can take a quick peek.
Kind of grays it out. See what happens.
So yeah, it gets rid of the major.
There you go. Yeah.
Major grid lines there, so it kind of just cleans things up. I mean, I like theme classic. I like theme light too. I mean, they're great default alternatives.
For different things.
Yeah.
And then the theme in here is just like a massive theme of like making it all pretty. So this is where she's actually picking some of the color palettes that she wants. So you can see there, the panel background and the plot background are going to have the same fill color to them, which is from her color palette. It's going to be number 1. So the first variable there, the first hex color in that color palette. Access lines, so that's why she did the classic, so that she could set her own kind of lines and things like that. So she's got access lines are going to be for the axes. The legend background is going to tell us how we want the legend to look. She's going to have it blend in with the panel background, so it's the same colors. The plot title, obviously, is going to, she tells it to H-just, so 0.5 is going to be that she wants it centered into the middle of the plot. The size is very large. The family that she wants is going to be the type of font, and then she wants it to be white colored. Plot subtitle is also going to be centered, a little bit smaller, but everything else, all the same rules apply. Legend text, this is now getting specific to the legend that she wants in terms of she wants white writing, calligraphy, font again. She has her certain size there, and then her axes, texts and title. So this is going to be specific to the X and Y axes. And she just passes to that what kind of color palette she wants and how large she wants it to be. Then bottom, she gives it a label, name, and X on the X and Y axis. She gives the label a fill color, so labs fill equal termination reason. And then she gives her a title and a subtitle. She runs it all and she saves the plot, so it's going to produce this really nice looking plot here.
Yep, exactly. So I was just kind of moving things around a little bit, just mentally how I might group things. Is I'm kind of theming things. I'll like do all my axes theming and then all my legend theming. Just, I don't know. I think sometimes it's easy to, there's so many options that exist that if you want, I don't know, I like to group them when I'm doing it. But clearly that all worked. And let's generate the termination plot, which is what she called it. And there we go. All right, so it's super visually popping. It's got the same color, that cool color palette that's based on the image there. You can really see the inspiration like for that coloring from the plot there, or from the image there. I think it conveys, like, look at all these successes there, or bad weather here in the lighter white. So I don't know, I think it's a great way to look at it. I enjoyed it.
And I guess I guess it's also not just the successes, but it's the number of climbs that are going on.
Yeah.
It's 'cause, like Everest, people always, I've never been there obviously, but people always talk about how it's becoming too overpopulated, and so obviously that's a lot more people climb, and then obviously improvements in success because of improvements in technologies, and also in training, like how these people physically prepare, and nutrition and what they can bring on the mountain and eat. I mean, there's like books on it now where there might not have been pre 2000 even. So,
Yeah, you mean the folks over here that were climbing like 19, what would be that, 1910?
they were like going up with the old
Canvas
school,
and
like tennis rackets on their feet, and
yeah.
like a walking stick. No real.
They're like, we're gonna make it.
Yeah, yeah. So it's
So
pretty.
yeah, so thank you so much, Kaylee, for letting us go through and explain how your code works and explain how to create the color palette, do all that awesome stuff. All right, so now we're gonna hop over.
I said really cool. Yeah.
Yeah. Alrighty, so now we're going to hop over and we're going to go through how we might analyze, the climbing expeditions, how we might approach it in a different way. So let me quickly restart my R session, and we can get going with that already. So let's clear that out. All right, we're ready to go. All right, so we've organized ours in an R Markdown like we usually do. So we've got our header at the top here, going, this is what we're working on. Patrick was the one that worked on this one, and started it a few days ago. We have our setup here, which is where we like to set our libraries. We're using Tidyverse, Tidy Tuesday R. I don't think we use Shiny.
I was going to, and I didn't. Delete it.
It's gone. Skim R for kind of visualizing data. Plotly for visualizing interactive data. ARM, LME4, and MER tools, and this is for modeling stuff that we do. We set the theme, so we don't have to go through and apply this to each one of our plots. We set it by default, the light theme. We are going to load in the data, and we will then assign it, read out each of the data sets out to peaks, expedition, and climbers. So we'll do that, and then we'll just kind of take a high-level look at the data. This is using Skim from the Skim R package. Like I said, it's incredibly information dense here, where it looks at the different variables. So we've got 76,500 rows, 21 columns. There's 10 character fields, 6 logical, 5 numeric. There's a fair amount of missing in death cause and injury type. Not too surprisingly, because if
you died, you didn't get to report how it happened.
Yeah, that, or hopefully there's a lot of successes, right? Like, I think in this data set there's a fair amount of successes, or not deaths at the very least. So, why would you need to have death cause if you succeeded? You didn't
True.
die. Then they've got some very logical types for fields like hired. So did the person going up there, were they hired or not? And then some numeric variables like year, so year of the expedition, age, how high they got, death if they died, and injury height if they got injured. So like I said, incredibly information dense, gives you like a kind of really high level look at the data set before you actually go in and start doing any modeling or anything like that. Then we're also going to take a quick head too, because that gave us a great summary, but sometimes it's also useful just to see what you're actually dealing with. So we've got expedition ID, member ID, peak name, year, season, sex, age. So this is like the different people that went up. Their role in the expedition, whether they're hired or whether they were the people paying for it. Great information there. Patrick, do you want to take us from here?
Yeah. So the exploratory data analysis piece, I just kind of was like looking at some things, really just kind of use this section to get my bearings. So ask a few questions like, what type of role do people in each expedition typically have? So obviously there's lots of climbers. The next group is a bunch of the group of Himalayan workers, right? So your Sherpas who are carrying all this stuff and kind of doing doing the hard work, like incredible, as a physiology a guy, that's like fantastic physiology. These people that live at these high altitudes and work and can be able to do this. You have leaders and doctors, also important, things like that. So first was just like, okay, who are the people usually going on the climbs? And then I also wanted to know, like, what kind of success has there been on the climbs generally? So I just kind of did a little count of the distinct first distinct peak names. So like how many times have these things been, how many expeditions have gone on rather in these climbs. And then we do the next one, which is counting peak and success. And then also doing a mutate there. So getting the percent of successes. So we just, and this is the, top 100, n greater than or equal to 100. Peak names. So we're just looking at success rates now and seeing like, okay, well, obviously right away, what stands out in the N column there is there's some mountains that don't have, what was the count? Oh, sorry, that's the success. So some of these mountains have different climb numbers, right? So as you just have to like take that into account. They're going to have different number of expeditions that have gone up certain mountains. So something like Everest might end up having a lower percent of death rate once we start looking at that. But that's because there's been so many darn people who have also tried to go up it. So there's a lot more observations, right?
Mm-hmm.
Which is what we go into next, which is our most common, the count of deaths on the most common climbs. So again, I'm just filtering out some of the most common climbs. And I want to grab the first argument here is just to get those most common climbs. So I want the main peaks. So I take the climbers data, I'm filtering out n equals or greater than equal to 200, counting the peak names and saying, give me only the top 10. Top n is 10. And then I pull those peak names. So if we run that and we run main peaks, we get a list of the 10 most climbed Himalayan peaks. Then I create this little data set called Main Peak Expedition, where I'm filtering out from the climbers data the peak names that are in those main peaks, so the main top 10 peaks. And then I'm creating this little variable here called died, which is the sum of died. So died is a binary column, a Boolean column of true and falses. So in R, if you have true and falses, you can sum those because the true is always looked at as a 1 and the false is always looked at as a 0. So that gives us a new column at the end of whether the person died or not. And then we just start to make a graph. Well, how many times do people die? And so obviously, as we saw in Kaylee's plot, there's lots of successes and there's few deaths, although it does happen. And so you can kind of see the counts across time. Then the next thing I did was I made a little plot here. So she used that like round any function, which I think I'm going to start using. I had to use the little modulus operator here to get my decade. So I take year, I minus year, and then the modulus operator for 10 gives us the decade. So it's going to move it up or down, constrain it to whatever decade it was in.
So a modulus is it's not a common operator. Like, it's common in computer science and that sort of stuff, but it's not like common. Like, I was never taught this in elementary school and stuff like that. So just to take a second to explain what a modulus is, it gives you the residual. So imagine dividing, 15 by 4. All right. So you end up, it divides it evenly into 4 3 times, and then you have a residual of 3.
A remainder. It gives you a
remainder. So like 3.75 is, so let's just do the modulo, which is the percent. it gives you 3, because that's what's remaining after 4 went evenly into 15 3 times, and then what's remaining after that.
So if you were to do like 2002 minus 2002 modulus 10, you'll see what happens here. And it's going to put us into the 2000th.
Yeah.
2000th decade.
Because 10 went evenly in 2002 200 times, and then you had 2 remaining. Sorry, I just wanted to make sure that people knew what that was.
Yeah, it's a tricky one.
Yeah, it takes a little bit of mind bending to think about this, but it can actually become incredibly powerful.
I think he stopped doing remainders after like 3rd grade, so
yeah,
forget that there's remainders.
What? What is this world?
So I make a plot. I make a plot here. I think this is the Plotly plot. So what I'm doing is I'm taking the main peak expedition data that I created. I use the modulus operator to create my decade variable because I don't want all the years plotted. It just kind of gets messy. I want the distinct expedition ID. So remember, we're dealing with like repeated people within this data set, or sorry, repeated expeditions. So if there was 10 people in an expedition, and let's say it's expedition number 1005, number 1005 will be repeated X amount of times, right? So all I'm going to do is I want the distinct expedition ID, and then I'm going to group by decade and peak name. I want to summarize the expeditions, so how many expeditions were going on, and I actually want to sum up all of the deaths that took place, so whether people died or not. I'm going to make this into a GG plot with x-axis is going to be the decade, and y-axis is going to be the count of expeditions over time. I'm going to use the label function to give me that value of deaths inside of the plotly that I'm going to plot. And I'm going to fill and color by the peak name. And I'm going to just make a simple geom line and point plot so that we can look at this over time. And so we run ggplotly. And here we get our little plot. So we can turn things on or off. This is like a totally clickable plot. Obviously, there's Everest at the top. Yep, you can highlight and move in. You can double click on in the legend on a certain, there you go. And then you can get its count of deaths if you were to click the dots as well. Yeah. So just a ggplotly is like a super easy function if you want to make like quick and dirty interactive plots. The other cool thing is if you click export on a ggplotly, you can do so up in the upper left there, export by the zoom function or by the zoom argument on the left.
Oh, here.
Yeah.
I was looking for it in the.
You can save as a web page, and it'll just save a simple HTML to wherever your working directory is, and email this out. So like I could save this as a web page and send it, in an email to Ellis and say, hey, check this out.
Look at all this cool thing that I did.
Look how many people climbed Everest in the past decade, and that's kind of cool.
Yeah.
Right?
There are the number of expeditions that happened, and how it's just like. So many people.
Yeah.
Cool.
That's kind of a fun one. Easy way to do it, ggplotly. Okay. So that brings us then to things, just some more exploratory data analysis. I was curious if age at all influenced death, just because I thought maybe this would be a variable that I could put into a model. And it's sort of a weird, I did a little thing there up in the climber's death there where I created an FCT lump for role. So if you remember, there was like leader, there was climber, there was Himalayan worker, leader, and then there was like everything else. So I just grouped into 3, and then everybody else is an other. And then I created also an age bin. For this, I used that cut number function, which will separate into the n number of quantiles you're interested in. I just had 4. And so this was just kind of strange with age. I wasn't sure if we could use this just simply because if you look at the age distribution in the plot right there below the table that I created. Well, this is age and death. So first of all, it doesn't look like it doesn't look like there's a big difference there. The distributions pretty much equally lay on top of each other.
I got too excited. Too many friends.
There you go.
That's what you're looking for?
Yeah, exactly.
It's
So there was nothing really there, and then I said, okay, well, what about if I look at the bins that I cut, the quantiles that I cut? So I made that little count right there, and same deal. And then I noticed, like, wait, there's people that were age 7 that did some of these climbs, and so I just kind of decided, okay, age isn't going to work. The next factor that I was interested in was season. So I said, okay, how does season influence the potential rate of death? And so there we see our trues. We could have filtered out just the trues to look at death, but we do see that winter has about a 1.9% probability of death relative to some of the other time periods. Spring, summer is 0.5% basically. Autumn is 1.0%, so you're getting close to winter time.
Mm-hmm.
And then death rate on some of the more populated climbs. So this is just, again, creating some tables and counts and some proportional tables, which I often use. Gives us the probabilities of death on these different mountains, those 10 mountains that we filtered out. And so that gave me some information to think about to start to try and model this data. So the next part is where we get into, we're going to fit a logistic regression mixed model. And so I'm just going to do this on the top 10 peaks that people were climbing in the Himalayas. And we're going to set our fixed effects to season, sex, whether oxygen was used, and the climber's role. And then we're going to have a random effect to vary for the peak name. And so the way I would probably explain this is if we just fit a logistic regression model straight up and didn't account for the peak name, we would be pooling all of the information across those 76,000 rows. And that's fine. That'll give us a model to basically go on and give us a probability of death. The tricky part is that we violate one of the assumptions of that kind of model, which is independence. And that's because we have repeated climbs on some of these mountains. And because we have repeated climbs, then we have to make the assumption that the probability of death is probably correlated within a mountain more so than across mountains. So there's probably a different probability of death on Everest than there is on any of the other mountains. And so with the mixed effects model, we can account for that. Our other option would have been to build a completely individualized model. So if we built a model for Everest, a model for each of the 10 different mountains that are typically climbed, that would be no pooled, right? So the first option is we pool everything. The second option is we pool nothing, and we have individualized model. And then the striking the middle ground is this mixed model where we say, you know what, we have these fixed effects that we think are going to influence the people across all mountains. But we also have this random effect for the peak name where we have multiple climbs about each mountain. So we know something about those mountains. So we're going to say that, okay, the fixed effects will behave similar in the population, and the random effect will allow the outcome of that model to vary depending on whether or not we know the person is climbing Everest or one of the other 10 typically climbed mountains. So we're going to run this mixed model.
And it takes a bit of time for it to run, right?
Yeah.
And this is so why is it taking a while?
Well, it's fitting a more complex model than just a simple logistic regression where it just has to basically identify, so like maximum likelihood estimation, right? It has to identify the outcome relative to the values that it sees. Here, it's trying to fit that kind of model, but also account for the nature of the repeated measures within each of those different peaks. And so it's okay, and there it just finished. And so it takes a little bit of time to kind of churn through that. And some of these models can get big and run for a substantial amount of time. Here I use the display function. It's a little bit cleaner than the normal summary function. That comes from the ARM package. which I believe was created by Andrew Gelman and some of his colleagues who are statisticians. He teaches at Columbia and has written a lot of books on Bayes and things like that.
Mm-hmm.
So we pull the display and we get our fixed effects and our random effects, or what's called error terms in this outcome. So the fixed effects, remember, we're working on a logistic regression model, so everything is on log odds here. So our fixed effects is giving us information about those variables that we specified within our model. Anything that's negative would be decreasing the probability, and anything that's positive would be, well, decreasing the log odds, and anything that's positive is increasing the log odds relative to the intercept. So remember, the intercept is mopping up any of the baseline values. So for example, season, we have season, spring, and winter. So that intercept is reflecting the autumn. It's alphabetical. Sex we have specified in the outcome as male, so that means in the intercept it's female. And then oxygen used is specified as true, which means in the intercept it's actually false. And then the role of the person is going to be the climber. So those are the intercept values, and all of these log odds are relative to those intercept values. The random effect, the error terms, tells us how the peak is going to vary based on, or how the intercept is going to vary based on each of the peaks. And so we can tease that out a little bit by looking at other aspects within this output. So that was display. If we looked at the fixed effects itself, those are the values that we saw exactly from the model. And if we look at the random effects, now we get the actual differences in each intercept relative to the actual model intercept. So there we see the fixed effect intercept as negative 4.91. So what we see here is, in the random effects, is the peak differences between that model intercept. So we would basically add these values to the intercept to get how the model behaves. And we can see all of this wrapped in one if we do the coefficient line there. So by doing coefficient, now we see, for example, Amidoblin has an intercept of negative 6.04. We could scroll up just a bit, and we would see that if we added negative 1.13 to negative 4.91, we're going to get negative 6.04. That's the intercept for that model. And now we see also that the other variables that are fixed effects within this model, they are the same. So we didn't allow the slopes to vary for this model. This is what would be called an intercept-only model. The slopes are going to be thought to be the same for each of the peaks. The only difference is the intercept. Okay. There's reasons why you might allow the slopes to vary. We could probably look into this model a little bit more and build other models and test them, but I didn't have time.
We have limited time to do this.
Yeah, we get what we get.
Patrick very kindly put this thing together. I don't have the stats.
We can. So because we're on a log scale, we can transform these back by taking the exponent, and now we're back onto a normal scale. So now we're working in normal odds. So for example, winter. Remember, above the intercept value is increasing, would increase the odds of death by 1.32 times. And that's a relative value. And so it's important to consider that because it's a relative value, we want to know on an absolute scale how much the probability of death changes. And to do that, we're going to need to tease apart the model a little bit. And we're going to do that in a second. The first thing I just wanted to show is how you can plot some of those random effects. So the random effect intercepts we can plot with the lattice package. We haven't talked much about the lattice package, but it is a pretty helpful package when dealing with mixed models, I find. And we just make this little dot plot of the random effects. And so this shows the 0 being the actual intercept. It shows how each of these peaks differ from the population, and then the standard errors around each of those. So obviously mountains that are climbed more, for example, Everest, have a much tighter confidence interval, right? It's much smaller because we're more certain about what we know about that mountain, given how many people have climbed it, versus Lhotse, I guess that is, Bar Umsi. Those have
These
much
two.
wider.
Yeah.
Yeah, much wider confidence intervals. And so we'd be less certain about the outcome on that model. So let's make some predictions on death. So as I said, the coefficients are interpreted on a relative scale. So that was 1.32 for winter, 1.32 odds. We want to understand these outcomes on an absolute scale. So we want to take the inverse logit of that entire equation. So I'm going to create a new climber, and this climber is going to be climbing in the wintertime. She is a female, obviously. She's brave. She's not going to use any oxygen. She's going to be the leader of the climb. And for the heck of it, she's going up Everest. So we have new data frame, and that is going to be this woman who's basically, she's going to use this model to figure out, we're gonna use this model to help her figure out when the best or safest time to climb so she can hedge her bets. I'm going to do this by hand so that we can understand some of the architecture, and then I'm going to show you how the predict function works. So I write this inverse logit function. And so this inverse logit function is going to take the output of our model regression equation, and it's going to turn it into a probability by dividing the output of that model, the negative of the output of that model, the exponent of the negative of that output of that model. So that's how the inverse logit function is going to work. So we create our function there. And now we're going to say we're going to get our results for the new person above. So again, I did this by hand. So I take the fixed effects intercept. I take the fixed effects FLME4 is going to be the season. So it was winter. The fifth variable within the model is going to be sex. I multiply by 0 because she's female. So we want the intercept. The next one is going to be oxygen used. I multiply by 0 because she does not use oxygen. And then the last one we're going to do is the leader because she's the leader. And so if we run this as just a regression equation, we get a value, negative 4.25. And we're going to stick that into our inverse logit function to get a probability of 1.4%, a probability of death. Now let's say that was if we were predicting this across the population, but we know she's climbing Everest. So let's show how the actual random intercept behaves. So we're going to pull out the intercept for Everest. So there's all of our intercepts. We're going to take the peak name of Everest, which is going to be a value of 0.16. And we're going to add that to our fixed effects within the inverse logit function. So like I said, the random intercept is going to vary from the population intercept. And when we add that in, we actually increased her probability from 1.4 to about 1.7% probability of death. So that's how it works by hand. We can do the same thing if you're in a rush and you don't want to do it by hand. We do the same thing using the predict function. So if I run the predict function, I get that same value, negative 4.25, because I set my type to link. I can then plug all that into their inverse logit and get the same information. If I want to get the probability out, R is smart. It's going to actually do this and transform it all back to me if I change the type to response. So here, change the type to response, and we get the same value, 1.6. So what we did by hand, we also got out by R. So what about prediction values? So what if we wanted a prediction interval? So we wanted to say, predict a range of plausible values. So we know the floor and the ceiling of death, right? So here I have a prediction interval set up. So the way this works in mixed models is we're going to use a bootstrapping approach. So bootstrapping is like a resampling approach of the data for however many iterations you want. Here you can see I set n.sims equals to 999. We could pump that up to 10,000. We could do whatever we want, exactly. But we just leave it at 999 for the heck of it. It's going to resample and the data for that many iterations, and then across that, we'll be able to produce our fitted value and then a prediction interval. And prediction interval is a little bit different than confidence interval. A confidence interval is making a statement about a population. A prediction interval is usually going to be wider than a confidence interval because it's taking into the fact that there's uncertainty within an individual. And so now we see that, okay, for this person, which was winter, male, no oxygen, a climber, and going up Everest, we have a 1.7% probability of death with a confidence interval at 90% confidence interval ranging from 0.4% to 9.4%. And so the cool thing about a model like this is that we can then begin to change the values to see how they look. So what if he says, man, 9.4% is kind of a high ceiling. What if I did it in the summertime? Okay, cool. So now we're down at the highest end. We're down to about 3.5%. So we've lost about 6%. And what if he says, you know what? I don't have to be so brazen. I'll go ahead and use oxygen.
I don't want to risk my life that
bad. Yeah. And so now we're down to 2.7%. And so we can change this around and mess around with it. The one last thing I'll say before we kind of end it is if we scroll up, you'll notice in the predict function right there that I did say allow new levels equal true. So if we went up to the new data frame that we have created on our female climber right there, and we change this to, let's say, peak name is Mount Ellis, which has yet to be explored.
I'm sorry, I'm not I don't go on expeditions. I don't have a mountain named after me quite yet. One day, maybe.
Name your own mountain. So if we said that, the predict function is smart enough when I say allow new levels to equal true, it doesn't, it's smart enough to say like, oh, okay, this is a new level. We've never seen Mount Ellis. So just go ahead and use the fixed effects. The best assumption we can make, and this is sort of, I think of a mixed model as like a gateway to Bayesian inference is that, or Bayesian modeling is that when faced with information that the model doesn't know, for example, this new mountain, the best estimate is the population estimate. Until we see more data, if you remember our lattice plot, until we see more data where the confidence intervals begin to shrink and we have more confidence about that peak, until we see that more data, the best option is to guess that it's going to be similar to what we would observe in the population, which would be a 1.4% probability of death. And so that's a little bit of an intro on mixed models.
That's so cool.
Predict whether or not we'll die.
That piece is less cool. But yeah, that's super cool. I mean, I've heard about mixed effect models and all that, and there's a lot of cool work being done on that. It's just, once again, I've not had the opportunity to really have somebody sit down and really explain it to me. So this is really helpful for me to like kind of understand. I've worked with these like kind of ethereal models before with some statisticians, but never actually had it explained to me like this and how to tease apart different relationships. So that's really cool. So yeah. Thank you for doing this. I'm sure all our listeners here will enjoy this as well. And I think we can call it. So if you have any comments, if you want us to talk about anything, please leave a comment down below or add us on Twitter at tidy_explained or either one of us. We love to hear from our viewers and want to learn more about what you're looking for out of us, because we want to give you we want to teach you, we want to give you the tools to use R and learn that, and we're really enjoying doing this. So with that, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And I'm Patrick Ward. You can find me on Twitter at OSP Patrick. And you can reach the both of us, if not on Twitter at tidy_explained. You can reach us on Gmail, if you prefer, at tidy.explained@gmail.com.
All right. Thank you, and keep on exploring your world.